Hello, everyone. Welcome to tonight's session. I to the computer. I don't know if it's streaming live. I had to reboot. Everything is very slow. And so let's start with the sound check. Let me know if you can hear me. I still can't get YouTube to open, but I have my software open. So I am not sure what is going on, but I'm hoping that this is at least working. Come on. Okay, I see that you can hear me. So I'm just going to have to stick with the backup software and, oh great, I can't even scroll my notes. Oh my goodness, what is up with this? Today is just a day for technical difficulties. So while I am trying to get that to, oh my goodness, that's going to be hard. I think I got it. Okay. While I'm trying to get all of that sorted out, let me know where you're tuning in from and when you are getting tested on this topic. Tamar, this Friday. Marks, it is good to see you. Valerie, this is the Valerie that I've been talking to in email, right? If yes, it is good to see you. Erica can hear me. Rachel can hear me. Aliyah, it is good to see you from all the way around the world. No, sorry, not around the world. You're local. I was confusing it with someone else, but I do recognize who you are. Welcome. So now that you're done with organic chemistry, what are you up to? Paris can hear me. Awesome. And in that case, Valerie, it is good to see you. All right, we are going to make do with very slow tech, but I think as long as you can hear me and see my screen, I think that is all we need. So let's call it a day and let's go ahead and get started. Let me know in the comments where you are tuning in from. I don't have the YouTube dashboard open. I can't get that to open. So I can only see what's going on if you leave a comment, because the comments are basically the only thing that's working right now. Balima, excellent. Oh, thank you for reminding me. Let me see if I can even get you that. Go. Okay, that I did get. So what Balima is talking about is you do not have to worry about taking notes today. Anything that you see me drawing, I will save as a PDF and email to you. Once the comments at any point, oh my goodness, where did my tablet go? Something went wrong. I know something went wrong. You don't need to tell me that. I'm talking to the computer, not to you. I just got kicked out of my streaming software, of course. Oh my goodness. It's just been one of those days. Let's try sharing that again. Present, share screen. If you are sitting through this and being patient with me, I appreciate you so much. We haven't done a live stream together in quite a few weeks. And of course, the first one back, nothing wants to work. Marks, it is very slow on my end too. But if you can see me, if you can hear me, I say let's make the best of this, because Fischer projections is one of those topics that some professors skip it. Some professors don't, and if you don't, you really do have to know all the information. So go ahead and put live notes in the comments. That way I will send you the PDF notes. I will give you a link to get the PDF notes after we're done. Hans all the way from Central Africa. It is nice to see you from all the way in Central Africa. All right, so let's attempt to get this show on the road, starting with this right here. All right, so what are we going to cover today? Before I show you an awesome shortcut for how to quickly figure out the relationship between these two molecules, are they the same thing? Enantiomers, diastereomers, we first have to take a step back and look at what the heck are we talking about with the idea of Fischer projections. Fischer projections are simply a way to represent three-dimensional molecules in 2 dimensions, just writing them out flat, and you can put all your substituents around it. The idea with Fischer projections is that if you're trying to draw a big molecule with many, many chiral centers, it gets really, really overwhelming. If I have something very simple, say I'm trying to draw a molecule that looks like this, and I draw it in 3 dimensions. Let me put some substituents around it. It's not a big deal to represent it like this. But if I want to show the chirality of a molecule that looks like this, and I have, let's put a bromine here, an alcohol, a methyl group, what else can we put? Another alcohol. The more substituents you add, the more chiral centers you add to the molecule, the more confusing it gets. And if you can simply turn this molecule into something very simple that looks like this, the presentation is a lot cleaner and a lot simpler. And of course, it makes it a lot harder for you because now you have to know how to actually look at the molecule and understand what it is. What is the chirality? What is going on? If you're just joining, welcome. Don't worry about copying everything down. Instead, just comment live notes, and I'll give you a link to get the PDF copy of everything that you see me drawing today. I'll email you after we finish tonight. Yes, even if you're watching the recording. So let's learn how to convert from a 3-dimensional molecule with all the dashes and wedges into the 2-dimensional Fischer projection. First, to show you what a Fischer projection actually is. If you look at this molecule, this is not just 2 lines. This is very, very specific. And to help us understand what we're looking at, we're going to enlist the help of Mr. Organic Chemistry. He's very happy to be joining us today. He's all formally dressed up, complete with a bow tie, and that bow tie is critical. That bow tie tells us that whatever is to the right and left of a Fischer projection, no matter how many chiral centers you have, are going to be coming out of the page. And so if I take this right here as my central carbon, to the right, we'll make this A, and to the left, we'll make that B. I have a bow tie. So let's make it a little more obvious that this is coming out like this. And that will be substituent B out of the page, substituent A also out of the page. And then the spine right there represents the up and down substituents. And these are going back into the page. So if we put X and Y, then here we have substituent X and Y. This is not the way you're used to seeing a molecule, and you're typically not going to draw it like this, but at least you can understand with that central carbon, anything around the Fischer projection has a very specific 3-dimensional orientation. You can see what is going into the page, and you can see what is coming out of the page. If I have more than one chiral center, let's move this here so we can keep Mr. Organic Chemistry in view. If you have more than one chiral center, it's the same thing. So if I have something that looks like this, then we simply have a second bow tie. I should probably use a different color. So we have a second bow tie right over here. And that means that this substituent and this substituent are both coming out of the page, not to mention the first bow tie on the top, like that. And then the spine is still going back. That means whatever is sitting at the top here and whatever is sitting at the bottom here is also going back and into the page. So let me see a thumbs up in the comments if you're with me so far on what the heck it is that we're looking at. What does this Fischer projection actually represent? And then, of course, we have to learn how to turn a 3-dimensional molecule into a Fischer projection. I am seeing the thumbs come in. Excellent. When we are going to turn a Fischer projection into a 3-dimensional molecule, or the other way around. There are quite a few different ways to do this. Professors will teach you different options. My goal for you today is to do the fastest, but also the most efficient method, because you do not have time for everything else. And so if we put substituents around here, A, B, C, and D, the way that I learned how to do this in class is option one. Option one is mental gymnastics, where you imagine that the molecule you're looking at is a book. And this right here is a page in the book, and this right here is a page in the book, and you kind of take this page and you open it up. So you open up the book and make this molecule, don't worry if you're not following, because we're not going to stick with option one. And you make the molecule look something like this. So when you open the book, D goes into the page, C goes into the page, but we took B and we dragged it all the way out here like this. We have A all the way over here like this. And now we can easily turn this into a Fischer projection that looks like that, where we have D, C, B, and A. If you followed along, I want a double thumbs up in the comments, because this right here, I went through it so quickly because I don't actually care for you to learn how to do this. This is not what is important. What we're basically doing here is taking the molecule, and then we're pretending it's a book. We're taking this thing and we're just opening it up. And there, that's your Fischer projection. Notice that this right here is going back into the page. Notice that this and this is now coming out at you. So this is going out of the page. This right here is your Fischer. You're up and down, you're right and left. You know what? I don't like that method. It is too confusing. It is too complicated, especially under pressure when you're doing this quickly on an exam. So if you are happy to cross out option one and go for a faster way, say yes in the comments, or just put an X in the comments, because I do not like option one. Option one was mental gymnastics. Let's go ahead and look at option two. Again, I'm teaching option one very quickly because I don't want you to do that. Option two, I kind of showed you already. Option two is a model kit. So you take the model kit and you build whatever molecule you have. If your molecule has 2 chiral centers, you build it. Then you rotate and rotate and rotate and figure out exactly what you need. You line it up like a Fischer projection. So notice I have the stem right there. This, oh my goodness, my tablet just turned off. What is going on today? I have 2 devices logged in, so we just lost device number 2, but I can still keep talking to you. So that is good. We're going to give that a minute to turn back on. So let's talk more about the model kit. I guess I can teach this a little slower now. So if I have a molecule and I built it with a model kit, to draw the Fischer projection, I want to have the stem in the middle. I want the substituents that are going back to be facing away. So notice that this blue one is going back, this blue one is going back. That's the spine. They're going into the page. So I have them on the top and the bottom. So notice it's starting to look like Fischer. And then to the right and left, you have to make sure they're coming out at you. So this is the bow tie coming out at you. This is the bow tie coming out at you. And after you have taken your time to build the model kit, to rotate it, to represent it like this, you can then draw the Fischer projection exactly as you see it. And hey, that is definitely a good way to get another accurate Fischer projection. Let me just log in here. Yes, I know something went wrong. It's telling me something went wrong. If you liked option 2, if option 2 made sense, let me see a triple thumbs up in the comments. And let's get this back up. Oh, did I lose my notes too? Great, I lost my notes. Where did this? There we go. I found my notes. Give me a moment. I'm trying to make heads and tails out of this thing. It is one of those days. Why does it not want to share my notes? I have my notes open. I'm looking at them. Just give me a moment, please, while I try to figure this out. Oh my goodness. Hang on. Bear with me, please. All right, let's try that again. It's not responding. This is a problem. Let's try that again. Let's try reconnecting my keyboard and seeing if it will respond. If you need a bathroom break, now is a good time for that, or a drink. What do you do when your computer does not respond and doesn't want to open any program that you're trying to open? Let's get out of tablet mode and see if I can figure out what's going on here. Technology at its best. It's not working. Why is that not Okay, restarting for the win. I think. Cross your fingers for me. While I'm trying to figure this out, I will give you some good news. I have been working today on a brand new Fischer projections worksheet. It is so brand new, it doesn't even exist yet, meaning I don't yet have it available to share. But by the time your people who are watching the recording and for the students who are here, it will be ready to email out tomorrow. So put worksheet in the comments if you want a copy of the brand new worksheet. It is going to be awesome. And because it is not finalized, if there's anything specific you want me to add, let me know. But worksheet in the comments, I think we're good. Cross your fingers for me. Are you still with me? Are we still here to learn Fischer projections? All right, so I will respond. Actually, let's do this. If you put live notes in the comments and you get the live notes, I will include a link in, words are failing me. I will include a link to the worksheet as well. I'll send you the notes tonight, the worksheet tomorrow when it's ready. And yeah, we are back. Let's go. Let's do this. Okay. Option 2 is the model kit. And as I demonstrated, it is very effective. The problem with the model kit, it's time consuming. It's a waste of time. It's confusing to know, is blue a methyl group or a hydrogen? Is white a methyl group or hydrogen? And you may not even be allowed a model kit on your exam. So as much as the model kit is helpful, let's go ahead and X in the comments if you want an even faster, more efficient way, because the model kit is not going to work. And this brings, what? What is going on here? What am I looking at? Why did that just do? I have no idea what is going on today. So I am going to start a new one of this. Just give me a moment because this is not working. We're going to outsmart the system, and we're going to fix it after the fact. So what am I looking for? Let me just think. Let me see if I can switch this. Okay, brand new page of notes. This is going to work, right? Oh, it's that kind of day. Are you still with me, guys? Despite the technical difficulties, let me know in the comments if you are still with me. I'm feeling fortunate that today's session is a harder topic because that means you're probably still here. Noelle is still here. Thank you, Noelle. I appreciate you very much. Here's what we're going to do with option 3. I am going to show you a way to do the 3-dimensional into 2-dimension. I'm going to show you how to look at it without a model kit, even though I'm holding one up. And this is the kind of method that will work even if you don't have that mental 3-dimensional ability. Because if you ask me, to this day, I still cannot go down in my basement and look up and say, that's the room that's above, because one floor goes this way, one floor goes that way, and my brain is not translating what I did when I turned down the staircase. And so when it comes to Fischer projections, you need to know it this quickly. And so here's what I want you to do. If we take that 3-dimensional molecule and we put the substituents on it, we'll call them A, B, C, and D. What I want you to imagine is that you are going to place your eye right here. So this is, let's try to draw an eyeball like that. That's your eyeball. These are your eyelashes. I know it looks like a bug. Here's what I want you to consider. So I have a random envelope on my desk. That is what I'm going to use to demonstrate. And I want you to imagine that this envelope is your paper and your molecule is drawn on the paper. And I want you to just look at the paper like this. So notice how I have the paper here, but I want you to pretend you're doing that. So I want you to take your face and kind of put it on the side of the screen and then ask yourself, if B is going into the page and C is coming out of the page, when you put your face on the side, which eye lines up with B and which eye lines up with C if your face is sideways, as if you're looking into that molecule? Thank you, Yasmin. After the technical difficulties today, it's good to see some support. I really appreciate that. Question. So the wedge and dash are always on the outside? No. This is going to be one of many, many different ways that you can represent a molecule. But if you can get the general idea, if you can understand what it is that I'm showing you, then it will make a lot more sense. And so as you're lining it up like this, I hope that you see that your left eye lines up with B. No, that's other left. Your right eye lines up with B and your left eye lines up with C. So again, you're turning your face to the side where I have that eye drawn. So that should really be a whole head like that. Some hair. And then your right eye goes with B, your left eye goes with C. This is not something you're going to do in a complicated way. This is not something you're going to waste time on. I just want you to see how you put your face on the side of this molecule. And the way that you're looking at it now is very simple. That's the top, that's the bottom, compared to where your eyes are. And so when you're drawing it out, A is at the top, D is at the bottom, furthest away from you, furthest away from you. B lines up with your right eye. So we put the B over here. C lines up with your left eye. And so you put the C over there. And that is your molecule. We did not need a model kit, and we definitely did not need any mental gymnastics. So it's kind of like deciphering Newman projections. Yes, same idea, because Newman projections is another three-dimensional thing that we kind of have to look at, hold it sideways, see what's on the right, see what's on the left. If this was a Newman projection, well, I would need more, I would need another group on it, but you can imagine that the circle is right there, and now we can do the same. Actually, this is exactly like looking at a Newman projection. Yeah. So this is how I get all my substituents on here. Now, you may get the molecule presented in a different way. Let's say you have your molecule drawn like this. Let's slide this down. Let's say your molecule is drawn like this. This is a very common format that you're going to see on exams. So let's say that's a bromine and a hydrogen. What do you do to convert this into a Fischer projection? Your face goes up here. So you're looking at it from the top. There's your eye, your nose, your mouth. You're looking down at it, and same thing. If your face goes into the page, you're turning your face that way. Then which eye goes into the page? Your right eye. Which eye goes out of the page? Your left eye. And then this is away from you. This is away from you. So the way that you would draw it is this would be the up-down of my cross, and attached to it I have a CH3. That would be, it's technically an ethyl group. So this entire thing is an ethyl group. So I'll just put ET for ethyl group. Over here, I have a methyl group. How did the left become the top? Because it lines up with my forehead. If I put my head above here, that's my forehead. That's my chin, top and bottom. And then bromine lines up with my left eye. Hydrogen lines up with my right eye, and that is the Fischer projection. So this is critical. Before we move on, I want to make sure that you followed what I did here with you turn my head and picture which eye. It's really all about just lining up your eyes. So if you're with me, I want to see fire emojis in the comments, and then I'll make it more complicated because your professor is not going to stop here. Your professor is going to give you much, much harder questions. Let's look at one from the other side just to make sure, again, we're on the same page. Let's say I have a molecule that looks like this. And here we'll put an alcohol. Here we'll put a hydrogen. And now you put your face right there. There's your eye, nose, mouth. So you have your forehead, that's the top, your chin, that's the bottom. So if we draw it out, forehead at the top was a methyl group. That's a CH3. Chin, bottom, that's an ethyl group. That's an ET. If I put my face under this thing, my right eye goes into the page. My left eye comes out of the page. And so right eye is a hydrogen on the right side. Left eye is an oxygen on the left side. I am seeing fire emojis in the comments. That means we are on the same page. Let's crank it up a notch and see what happens if you're given a molecule now that looks like this. I have an OH and an H. And then here I have a bromine and a hydrogen. Now I have a molecule with two chiral centers, which we already saw would be a Fischer projection that looks like this. But the question is, what the heck is going on? And how do I do this? Option 1, mental gymnastics. We're not going to do that. Option 2, build it on a model kit. Build it, figure out what substituent is what, rotate it and draw it. We're not going to do that either. Now we have options 3 and 4 here. I'm going to show you both. 3 takes longer, but is probably more accurate. 4 is the one I want you to walk away with because no one has time to do 3. If I am looking at this molecule. For the Fischer projection, I need bow ties. I need both sets of substituents lined up like this, coming out of the page at me and like this, at me and at me. And so what I can do is take my molecule on paper and do a 180-degree rotation. This is something you should be comfortable with. I'm going to do it with you slowly. If I rotate the lower half of the molecule, then the upper half does not change. I have an alcohol here. I have a hydrogen here. This is the piece that rotated. And if everything rotated, we did it in that direction. We're looking to get two substituents at the top, so 180 degrees. If 180 degrees is exactly, whoops, hit my head, is exactly halfway around the circle. Up goes down, out goes in. So let's remember that. Up in the plane of the page, let's make this green, is going to go down in the plane of the page. Down, but on a wedge, is going to go up, but on dashes. And down on dashes is going to go up on a wedge. So again, 180, up is down, in the plane stays in the plane, out of the page goes into the page goes out of the page. This is the result of a 180-degree rotation for the green for the second half of the molecule. The reason I did it like this, and let me know in the comments if you followed, is because now I can take this molecule and very easily put my face right over there with the trick that I showed you. And then I can line up my eyes and say that my right eye is going into the page. So right eye would be hydrogen, right eye would be bromine. Left eye is coming out of the page, so left eye would be my alcohol and left eye would be my hydrogen. Let's go ahead and draw this. Let's actually draw it next to it right here so we can see. If my face is lined up that way, then my forehead goes to the top, which is the blue methyl group. That means I have a CH3 at the top. My chin goes to the bottom, which is a green methyl group. That's a CH3 right here. Going into the page, all my dashes go with my right eye. So on my top dash, I have a hydrogen. On my bottom dash, I have a bromine. Then on the left side, my eye that is coming out of the page, I have on the top an alcohol, and on the bottom, I have a hydrogen. This was kind of complicated, but pretty straightforward. And so if need be, this is how I want you to do it on exams. Let me know in the comments if you're with me, if this makes sense before I show you a faster way. Now, what I'm showing you is a couple of examples to demonstrate, but ultimately the way to really get this is to do tons of practice. That's where the brand new Fischer projections worksheet comes in. Just put worksheet in the comments and I will respond with a link to download the worksheet. Yes, even if you're watching the recording. If you followed me up to here, but you want to make this a little bit faster, put shortcut in the comments. Because if you got this right here, then the faster way is going to be just as doable for you. So here is what we want to do with the faster way. Let's go back to the initial molecule that we used to start the rotation. And let's draw what will be our Fischer projection. I kind of ran myself out of room, so we're going to do it in a little bit smaller. But I want them all to be together, so I'm cramming it into the screen. What we're going to do here is choose one chiral center to focus on. And from that chiral center, we will build the rest of the molecule with the same shortcut. So put your face at the top right here. That is a backwards eye. There's the eye, your nose, your mouth. And then start with a chiral center that perfectly lines up with your eyes. That means the upper chiral center here has this facing away from you. Forehead means the top. That's a CH3. Your right eye goes into the page. That's the hydrogen. Your left eye comes out of the page. That's your alcohol. And your first chiral center is exactly as we've done it before. It's exactly the same. Nothing changes. We are good to go. And look at that. It's exactly the same. Now, for the second chiral center, instead of taking the time to redraw the molecule, rotate this 180 degrees, here's what you can do. You're not going to rotate it in your head. No mental gymnastics. I promised you none of that. We're instead going to use the logic of the mental gymnastics, and we're going to say, if I took the time to rotate this one right here, then the two substituents going down and away from me are going to be opposite of what I see them. Because if the hydrogen is down into the page and lines up with my left eye, because it's facing away from me, if I were to bring it up, it will go to the other eye. And so what you're going to do is compare what you have over here and do the exact opposite. That means if OH is on a wedge left eye, if it's facing away from me, then the dashes are going to be left eye. If hydrogen is on dashes right eye, if it's facing away from me, then the right eye is going to be the wedge. So do you see how all I did for that second chiral center is switched it? If the wedge was left, the wedge is right. If the dashes were right, then the dashes are left. And then all I'm going to do is draw it as I see it. So we're going to draw these in green. And we said that hydrogen is left. Bromine is right. The methyl group facing me is still my chin. And wait a minute. Is that not exactly what we have here, minus the extra step of redrawing, twisting, and then doing the whole thing? So again, a slightly more difficult method, but if you practice this a few times, this is going to save you so much time and is just as doable. So let me know which option you prefer, the rotation, the redraw, or the mental rotation. And it's not even a mental rotation. We'll call it the flip method. So we'll call this one the redraw, and we'll call this one the flip. So in the comments, which one you are going to stick to. Question: does it matter the way that you're writing it? If I see you're using OH and then HO. No. So that is a very good question. And a lot of students get confused. For example, what you'll see me draw sometimes is if there's a line, say the end of a molecule, this right here is a CH3 group. Sometimes you'll see it written as H3C, or in this case, you see me write it as HO or OH. It's the same thing, but the idea is if I wrote this as a CH3 group, you recognize it as what it is. But if I write it as an H3C, what I'm really saying is this H3C. So it really does not matter. It's the same exact thing. I have seen students get confused, and that's why I took the time to explain it. Let me know if this makes sense. So let's take a look at what I did here. I have this one as an HO. I wrote them both as an HO in this case because it's simply an O attached to an H in that direction. But bromine is obviously Br no matter what, and so I'll never write it as Rb because they're not two different molecules. I am seeing flip method, flip method. I encourage you to try the flip method because with a little bit of practice, it is the faster and more straightforward way. Greetings from Germany. Hello from all the way around the world. All right, so we have our method for drawing it. If you want to turn it back into a three-dimensional molecule, that is very easy because all you're going to do when turning it back into 3 dimensions is say that if this is what I have, and I have A, B, C, and D, I could do whatever I want with it. If your professor specifically wants you to put it onto something that looks like this, then you can use that eye trick again and say, if my face is over here and this is my eye, forehead, that's the top, chin is the one all the way away from me, that's the bottom, so that'll be C. And then where do my eyes go? This is my right eye, this is my left eye. My right eye gets the right one, my left eye gets the left one. And there, I just turned my molecule into, my Fischer projection into 3 dimensions. If I have to do the same thing for a Fischer with 2 substituents, I want to show you how to go straight to the zigzag because that one students find the most difficult. So let's move this down. Let's give it some substituents. We'll go with a CH3, Br, H, Cl, H, Et. First thing I see is my carbon chain is 1, 2, 3, 4, and 5. Ethyl is 2 carbons. So I'm not even looking at the Fischer right now. I'm just drawing a carbon chain with 5 carbons, numbered 1, 2, 3, 4, and 5. Now let's see how to put the 3-dimensional substituents on it. I'm going to start with 2. And if I make 2 3-dimensional, then I am going to have a wedge on here and dashes like that. And so if I put my face on the top, then I have my eye, nose, mouth like that. That's my chin. So that's carbon number 1. I'm sorry, that's not my chin. That's my forehead. There's my chin towards carbon number 5. And my right eye goes into the page. My left eye comes out of the page. Right is a bromine and left is a hydrogen. As soon as I have that first chiral center, the rest will fall into place because 3 is exactly opposite. For 3, it's away from me, and so I'm going to flip it. If right was bromine, then Cl will do what the right one is doing. Meaning if the right was dashes, here the right will be a wedge. It's exactly the opposite. And the wedge is the right in this case, or we could have looked at it from the Cl from the left. That is how I turned it into 3 dimensions. If your professor did not ask for a specific way to draw it, here is another option you could have done. Let's move that away. You could have just started with these 2 carbons, carbons 2 and 3 like this, and we're just going to turn that into a 3-dimensional Fischer projection like this. 1, 2, 3, 4, 5, and watch this. Why are my wedges looking drunk? There we go. 1 wedge, 2 dashes. Now it's very obvious if my face is up here like this, eyes, nose, that's a mouth. I know it looks a little bit crazy. Forehead, chin. Let me make it look like it actually is a face. So there's the mouth. This is the eye with eyelashes. And so my right eye is into the page, right eye is into the page. And that means right is bromine and hydrogen. Left is hydrogen and chlorine. Let's see if it matches up. It does not match up. Why does it not match up? What did we make a mistake? So we have the right side is bromine and hydrogen. Bromine and hydrogen. The left side is hydrogen and chlorine. That looks good. So what did I mess up here? I must have messed these up. Hang on. So if we have the right is bromine into the page, so then the right should be out of the page. So that should be hydrogen out of the page and chlorine into the page. That's what I had messed up. So the trick worked. My brain didn't, but the trick worked. All right, let's see. I went very fast, so maybe we should do another one slower first. Is the flip method the logic behind flipping RNS? No, we're not flipping anything here. We're just rotating, and we're saying that if I'm rotating, if white and blue are facing away from you, a full rotation brings them to you but swaps their position. Notice blue is on this side, but a full rotation has blue on this side. It moves positions. And so what you're saying is when it's facing away from me, blue is here. So I know that if I turn it, then blue is here. That's the idea with the flipping here. Let me know if that's clear. Okay, so then, hello, all the way from India. This is hard. Yes, this is very hard. And I went fast and messed it up. Should we move on to another concept, or do you want to see another practice problem a little bit slower? Because this was hard. This is definitely not easy. Noelle is on fire. Let's do this. Noelle says another concept. And of course, you can always rewatch this and do lots of practice with the worksheet as well. So, oh, I see the next comment, another practice problem. How about we do a different kind of practice problem? And that way you get to cover all the different things. Stereochemistry, which is what had just come up in the last question. So let's take a look at how to find stereochemistry on Fischer projections. I am horrified that the way some professors have taught stereochemistry is you take the Fischer projection, you turn it into 3 dimensions, and then you find RNS. I'm sorry, that's a lot of extra work, and we are not going to do that. So let's do a quick review for stereochemistry. Step 1, you want to rank your substituents. Hopefully, let me know in the comments if you are comfortable with stereochemistry in general, and that way I'll know if we could jump ahead to Fischer. Step number 2, you're going to ensure that number 4 is in the back. We are going to trace an arc from 1 to 2 to 3. We are going to rank substituents, get number 4 in the back, trace an arc. I feel like I missed a step, but this looks like what we have to do. So let's go for it. If the top of the arc goes towards the right, that is R. If it does not go to the right, it is not R. It is S. Stephanie, you covered Fischer projections before stereochemistry? That is bizarre. But hey, you get a quick preview here, so let's go for it. Let's do a molecule first with 3 dimensions, just to review. Let's say I have hydrogen, methyl, bromine, and alcohol. We're going to rank using the Kohn-Ingold-Prelog system. This is where it helps to have the periodic table memorized, but these specific atoms, H, C, N, O, F, Cl, Br, I, sulfur, phosphorus. Let me know if you've already memorized them, because this is something I stress over and over. And here is a perfect example of how it saves you time, because you can just reference this without having to go to the table. But we're going to make this even easier. As I teach in my stereochemistry videos, hydrogen is always going to be number 4. We don't even have to worry about it. Methyl in the presence of hydrogen is always number 3. That means we're really just comparing bromine and alcohol. Bromine outranks alcohol. That's number 1. Alcohol is number 2. That's what we forgot. We want to cross out number 4. I knew there was a missing step. Step 3 is cross out number 4. And step 4 is to trace an arc from 1 to 2 to 3. And that would go in this direction. Top of the arc goes not to the right, so it is not R, meaning it is S. And this is how we solve 3-dimensional stereochemistry. Erica, you are very welcome. Do you know the finger method? I don't. I like to keep things very simple. No model kits, no mental gymnastics, as you saw from today, and no like right-hand rule in physics. That's all confusing. I like to keep things on paper as much as possible because it makes it easier if you don't have those mental gymnastics. We are going to take the same rules and apply them towards a Fischer projection. And Stephanie, if you haven't covered this yet, I recommend, whoops, why did it go there? I recommend just kind of taking this all with a grain of salt. And instead of trying to learn it, just think, do I kind of follow what's going on here? Then when you get to this when you get to stereochemistry, it's going to be so much easier for you. So what we're looking at with a Fischer projection is if I have a molecule, and let's do this one right here. So we'll put a carboxylic acid. Any MCAT students alive on here today? And if yes, bonus points if you can tell me what amino acid I am drawing right now. Why am I drawing this so small? Let's draw this bigger. There we go. If I want to find the stereochemistry of this amino acid, I'm just redrawing everything in bigger, then I will have to rank again with the Conival-Prelog system, but let's use the shortcuts. Hydrogen is always number 4. Methyl in the presence of hydrogen, always number 3. Now I'm just comparing carbon to nitrogen. Carbon is lower than everything except hydrogen. So nitrogen beats it for priority 1, and carbon with the carbonyl is number 2. Now, I did not compare carbon to carbon as you would in stereochemistry because the trick, methyl in the presence of hydrogen, is always number 3. Saved me that step. But if you didn't know that trick, then you're looking at carbon compared to carbon. This carbon has an oxygen. This carbon has a hydrogen. Oxygen beats hydrogen, and that means the carbonyl is higher priority. So that's another way to do that. I am seeing 2 guesses starting with an A, and you're both correct about the A for which amino acid this is. The trick here is it's the second smallest amino acid. The glycine has the hydrogen. That's achiral. What is the next smallest group? It's the first letter of the alphabet because it is the first smallest amino acid. Hint, it starts with an A. All right, so now here's the problem. If I remember that a Fischer projection, like Mr. Organic Chemistry, has the bow tie, then this right here is coming out. And so I ranked my substituents, but number 4 is not in the back. The back would be the spine. Number 4 has to be the top and the bottom. Alanine. Yes, this is alanine. Absolutely correct. Number 4 is the spine, the top and the bottom. And so I need to get number 4 either to the top or the bottom. This is where the swap method comes in handy. Absolutely correct. As I teach in the stereochemistry videos, we are not going to swap the entire group. It's too messy. We're just going to perform an even number of swaps where the numbers get swapped. The first swap is putting number 4 in the back. In this case, I'm going to put it down. That means I bring 3 here and 4 here, 1 swap. I need an even number of swap because then I get the enantiomer of the enantiomer, which is the same thing. And that means I could swap anything else as long as I don't touch number 4 again. And so I'm going to choose to swap 2 and 3. So that's 3 and 2. That's an even number of swaps. That means it's the same as what I started with. Now I have number 4 in the back. I can go ahead and cross out number 4. Let's cross the number itself, not the group. Trace an arc from 1 to 2 to 3. Top of the arc goes to the left, and this is L. I'm sorry. Oops. This is S. For my MCAT students, I was going to ask you if this is D or L. Kind of slipped over there. The trick is put your carboxy at the top, substituent at the bottom. Hydrogen and nitrogen go on the straight. And if your nitrogen is on the left, it is L. If it is on the right, it is D. So fun fact there about your D and L amino acids. This is L-alanine. Or S-alanine, because that is what we're looking at here. Are you with me on how to find R and S when we have it in a Fischer projection? Because if yes, let's try a bigger problem. The same approach works when I have more than one chiral center. So if I have CH3, Br, H, I don't know why I keep going to the bromine and the OH today, but that's the groups we're looking at. We have to look at each chiral center individually. Questions. Is this something you cover in chemistry in high school? I have no idea. I did not even know organic chemistry existed in high school. I only learned about it in college. So if you're covering Orgo in high school, you'll have to find out. I don't know. Asia, that's for you. Can you explain the flipping of subs again? So one of the videos I gave you for homework was to review the swap method. And if that is something that you're not comfortable with, make sure you go and review that. If you put live notes in the comments, I will send you not only the notes, but also any resources mentioned today, including the homework. And that way you can review the swap method. But the gist of it, because I don't want to leave you completely hanging, is what I do. One set of swaps, enantiomer, second set of swaps, the same thing. So let's start with the top chiral center and rank our substituents, keeping in mind that this entire group is a substituent for this carbon right here. Let me see if I can isolate this and kind of move it down, give us a little bit more space in the middle. There we go. For the upper chiral center, let's start with the obvious. I have a hydrogen, that is number 4. I have a methyl group. Methyl in the presence of hydrogen is always number 3. I have a bromine, which outranks, let's light blue, so let's make this one purple. Bromine outranks the purple carbon, so that will be number 1, and the purple carbon is number 2. So I'm just going to put it 2 close to here because I want to keep the bottom half clean for the second evaluation. I did this fast because I know that methyl in the presence of hydrogen is 3. But if you did not know that, if you had a longer molecule, a longer chain, what you do is you look at carbon and carbon, both coming out of this carbon right here. The upper carbon has hydrogen, the lower carbon has other things on it, making it higher priority. That's how we got the 2 at the bottom. Let's keep this red so our colors are not all over the place. We need number 4 to be in the back. We need it to go down. And so I'm going to do 2 swaps, and the swaps from the top and bottom are separate accounting. You cannot mix those accountings. And so I'm going to put swaps at the top for the blue chiral center in blue. And I will swap number 4 to the bottom. So that gives me 4 and 2. Then I'll swap the other 2 just to keep it clean. And I'll put a 1 here and a 3 here. That is 2 swaps. It is even. I am good to go. Let's cross out number 4. Trace an arc from 1 to 2 to 3. And the top chiral center is S. Now let's move down to the bottom and do the same thing. What do I have? Hydrogen is always number 4. Methyl in the presence of hydrogen is 3. Or I could see that this is a carbon with hydrogen on it, but this is a carbon that I'm comparing to with a bromine, higher priority. So that means that oxygen is 1, carbon with stuff on it is 2. And once again, hydrogen has to go to the bottom. So let's do, not hydrogen, number 4. Hydrogen happens to be number 4. So let's do swaps. And the swaps here are going to be, let's do a different color. We will put 4 to the bottom. So that'll be 4 and 3, 1 swap. 2 and 1. That's the second swap, making it even. Now I can cross out number 4, trace an arc from 1 to 2 to 3, and the bottom chiral center is also S. I know that was very involved. I promise you, this is faster than redrawing into 3 dimensions and definitely less confusing than a model kit. Rachel, for you. Moch, just email me because that is definitely coming up, maybe even next week. I'm thinking about it. So this right here was the harder way, and obviously you're going to need more practice. I'll have Fischer with multiple chiral centers on the worksheet, so worksheet in the comments. But now I want to focus on a different type of chirality question, because professors like to do things like this. If you have Fischer projection number 1 and Fischer projection number 2, and they have, let's go with alcohol, bromine, hydrogen, methyl. Alcohol, bromine, hydrogen, methyl. And the question is, are these molecules completely the same or are they enantiomer? Question. Down means in the back, yes, because if we look at Mr. Organic Chemistry, who is very happy to join us here, Mr. Organic Chemistry wears a bow tie to remind us that right and left, like the bow tie, comes out of the page, and the spine is the wedges go down into the page. Right and left bow tie are your wedges, the spine are your dashes. Did I say wedges? I meant dashes. Dashes going down into the page. When you see two molecules like this, you're typically not asked to tell if the two molecules are R or S. You're just asked for the relationship. The way I have seen professors teach you how to solve this is build a model kit and find if it's R and S, waste of time. Mental gymnastics, waste of time. Redraw this in 3 dimensions, waste of time. The proper way to do this is to solve this one for R and S, solve this one for R and S, and if they're both R or both S, they're exactly the same. If one is R and one is S, then they're different. But if you are not asked if they're R and S, I'm going to argue I don't care if they're R or S. What we're going to do instead is the swap method as follows. If this is molecule A and this is molecule B, how many swaps will it take to make molecule B look like molecule A? And that is how we'll know the relationship. So A has an OH up there, swap 1. A has a methyl group over here, that's swap 2. And we have OH, methyl group, hydrogen on the bottom. There we go. Hydrogen, bromine, swap 3. I had to do an odd number of swaps to see B look like A. And if an odd number of swaps is how many swaps it took to make one molecule look like the other, odd is enantiomer. And I don't know, nor do I care if these molecules are R or S, because the swap method is the way to do it. Let me show you another one. Actually, another tricky one. Let's say I give you 2 molecules again to compare, but this time I'm going to put OH, H, let's mix it up, Cl, NH2, OH, H, Cl, NH2. We can do the swap method, and I'll get to that in a minute. But notice that if I follow the pattern OH-HCl-NH2, OH-HCl-NH2, are these molecules exactly the same? It's just a 90-degree rotation. 90 degree, if I take the whole thing and I turn it 90 degrees, then I have the same exact molecule. Does that mean that the molecules are enantiomers, or are these molecules exactly the same? Let me know in the comments. If you don't know, just put IDKY for I don't know yet. My question again is, are they enantiomers or are they exactly the same? And while you're typing that in, I want to show you something. If this is a three-dimensional molecule and I am holding it like a Fischer projection, that means whatever is in the up and down is facing away from you. Whatever is on the right and left is facing towards you. If I take this molecule and I rotate it 90 degrees, that is not a Fischer projection. That is not a Fischer projection because these are coming at you and these are going to the back. And so to turn this into a proper Fischer projection, I have to flip it around. The chirality reversed. 90 degrees reverses chirality because you can't just take a molecule that has wedges like this and say, now the wedges are like that. And so the trick here is that if the molecule looks exactly the same but a 90-degree rotation, these molecules are enantiomers of each other. They are not the same thing. Let's prove it with the swap method. So we'll see how many swaps it takes to get these two supposedly exactly the same looking molecules to look exactly the same. A and B. We're going to make B look like A. So we'll start by moving B look like A. We'll move the OH up and the NH2 here. That's one. Now let's get the H in place. So basically the NH2, we're playing musical NH2. Now the H is in the right place. Then we'll have green we haven't used yet. So we'll move the NH2 again. So we have NH2, Cl. That looks drunk. There we go. So we have an odd number of swaps to get B to look like A. And what is odd? Enantiomers. Right? So these are enantiomers, even though all we did was rotate the molecule, but you can't just rotate a Fischer projection. In general, it is recommended to use hardware molecule model sets. It really helps to understand better. You can touch and tinker. I'm going to give you a caveat warning with that. I absolutely agree. Notice that I am teaching with a model kit because I think they're highly, highly beneficial. I have ADHD. I need to touch things and I need to rotate them. So if I'm trying to explain this to you without the kit, it would be very hard. But look how easy it was for me to rotate and show you and flip and turn and all of that. But after you're comfortable with the concept, I want you to ditch the model kit and just be comfortable doing it on paper, because your exams are on paper. You do not have time to build a model kit. And that's even if you're allowed to, because some professors don't allow it. We were allowed a model kit, but I found it to hurt more than help because now I'm relying on something else. It takes time. It's confusing. It's faster to just know it on paper. Crazy how my professor never taught us this. Professors, we're not going to start that conversation, but let's just say I have a lot to say about some professors. All right, so now what I want to do is go back to that very first problem that I opened with, and I promised that I would show you a faster way to do that. So let's take a look at these two molecules. And what your professor could ask with a problem like this is not to find R and S. Your professor is going to ask something like, what is the relationship? Are they the same? Are they enantiomers or diastereomers? And so option one is to find R and S, which over here is going to be a lot of work. Option two, we're going to do swaps at the top. We're going to do swaps at the bottom. They don't connect. Swaps at the top have nothing to do with the bottom. And we're going to see how many swaps it takes to make molecule B look like molecule A. So molecule B has the methyl group in the same place. That works. OH has to switch. So H and OH for the top, I did one swap. That was an odd number. They look exactly the same. The top chiral center, these are mirrors of each other, mirror images, opposites. Now let's look at the bottom. I have a bromine on the left, so let's get the bromine there. That's one swap. I have, what color do I want to use here? Green. So the reason I'm doing this in color, just by the way, I have ADHD. Can you imagine the entire session like this? I don't know about you, but me teaching it, I know this information, I would not be able to follow. And so I try to do everything in color where if you're not able to fully focus on, because there's so much going on, at least you have just the colors that follow. You know exactly what is where based on the colors. And once we get into mechanisms, I will try to do the arrows and the electrons with the same colors as well. Erica, yeah, we need color, right? Hello, Tim. It is good to see you. All right, so we have one swap putting the bromine on the left. The next swap we'll do is going to put the methyl at the bottom. And that has everything lined up. This is an even number of swaps. That means that these two are the same. If the top of the molecule is opposite and the bottom of the molecule is the same, that means one chiral center is different, one chiral center is the same. That makes these two molecules diastereomers, where di-stereo, two types of stereo, some the same, some different. That is the relationship between them. We didn't find any R's, we didn't find any S's, and we didn't care about any R's or S's. What do you think? Swap method or finding RNS, or worse, turning it into 3 dimensions, then finding RNS, and then finding the relationship? I kind of know your answer, but let me know in the comments. Eric's question. So 90 degrees is always enantiomers if everything else is the same. So let's go back to this one right here. If they look exactly the same, but all it is a 90-degree turn, then yes, they are absolutely enantiomers. I know we covered a lot today, and it is a lot to process. Don't worry, I've got you covered. Put live notes in the comments for a copy of everything that I wrote today so you can follow along. Yes, even if you're watching the recording, and put worksheet in the comments for even more practice with my brand new Fischer practice worksheet. Lots of problems related to what we did today so that you can really get comfortable with all the different tricks. If tonight's session made Fischer projections finally click, yes, you're still going to need to review and practice. But if it finally made sense, I want you to imagine having this level of clarity where everything just clicks for every topic in Organic Chemistry 1 and 2. That's exactly what you get with my Organic Chemistry Study Hall. It's over 100 full-length sessions, beginner to advanced, Orgo 1 to Orgo 2. Step-by-step solutions, video solutions for all of my practice quizzes, all of my brand new worksheets, and we're slowly doing live solve with me sessions to work through the worksheets together. And of course, the ability to get help. So you're not doing this alone. There's a supportive community, and you have help from myself and my TAs every single day. When I took organic chemistry the first time, I was failing because I was lost, I was overwhelmed, and I was trying to do it alone. So I don't want you to have to do that. If you want this kind of help and you're tired of doing this alone, just go to layerforsci.com/join, and I'd love to have you there. Of course, it helps if I have the right link. There we go. layerforsci.com/join, and that's where you'll find details and be able to sign up. All right, I'll stay for a couple of minutes of Q&A, and then for anything else, YouTube keeps me connected for about 10 minutes. With today's technical issues, I don't know exactly what to expect, but I'll hang out in the chat for a couple of minutes after logging off to answer questions. But I'll start with the questions here first. The live notes comment is the live notes link is right there. For the worksheet, it is so brand new. I don't have it linked up on like when you sign up and you get the stuff automatically sent to you. I don't have all that linked up yet. And the way I'm feeling right now, I'm probably not going to finish it today. I am exhausted. It's been a long day. But I'll have it to you by tomorrow midday. So if you sign up for the live notes, then tomorrow I will follow up. Just anyone who puts their email in for the live notes, I'll also send you the worksheet. Okay, questions. Oh, Sanjana, I just realized who you are. You're the student I was emailing, right? I tried to email you. I don't think you got my last email, but I just realized who you are. Can you do RNS in a molecule? Erica, I don't understand your question. Do you mean RNS for a Fischer projection or RNS in general for stereochemistry? Because I do cover stereochemistry in detail everywhere. YouTube, study hall, worksheets, quizzes. It's one of my favorite topics. Noel, and I'll also post this to the study hall. Since you're a member, you'll get access to it there. And then sometime this week, I'm probably going to put a poll in the study hall to see which Solve With Me worksheet students want to do. And I'm thinking it'll probably be this new Fischer, or I don't remember if I have the substitution elimination solved yet. So that's another one that I'm going to put as an option. And you get to vote, and then you get to join me live for the session. You are very welcome. Can we do Diels Alder reaction? That is a fun topic. I don't know how many students are doing Diels Alder. Why don't you do this? Email me and let me see what I'm going to put on, because sometimes I'll do a poll, but this is a topic that my study hall members were asking about. So that's why I just decided to do this last night. That's how quickly this was planned. And then all the technical difficulties today, I had nothing to do with those. I don't know what was going on. Like nothing wanted to work today, but I appreciate that you guys stuck around because I think we turned out to have quite a good session after that. Can you answer this, please? So the top is an enantiomer because it has one swap. The bottom is a diastereomer. Oh, no, be very careful. So an enantiomer or a diastereomer refers to the entire molecule. Molecule A to molecule B, what is their relationship? And their relationship is they are either the same, enantiomer, diastereomer, or completely unrelated. If we have a situation like this, where the top half of the molecule are mirror image. Notice I'm not calling it enantiomers. I'm calling them mirror images. The top half is a mirror and the bottom half is the same. The molecule is not an enantiomer because an enantiomer would be a complete mirror. It's not the same because everything would have to be the same. It cannot make up its mind. It is of two minds, of diastereomers. So if it's half the same, half different, or you can have more, but at least one the same, at least one different, that's where you get diastereomers. No, well, that's actually what I think is going to come up next. I think enough students are on that. So, but I'll post about this more. All right, guys, I am mentally fading. So let's do this. I'm going to log off, get the notes together for you. I'll email that to you within like half an hour or so. I'll hang out in the chat as I'm setting up the notes and everything. So any other questions you have, type them in. Worksheet will go out tomorrow and we'll potentially solve this live very soon. So keep an eye, study hall members, keep an eye on the group for that as well. Thank you everyone for bearing with me through all these technical difficulties. I love this topic. So I'm so glad that I did not have to cancel today because everything was just not working. Tim, I'm not sure. I have no idea what you're talking about. My technical difficulties, I think, were with my computer. So first the computer wasn't working, then I couldn't get YouTube to load, and then my computer shut down. So it's been that kind of day. Erica, not yet. It's brand new. Like, it's so brand new. There isn't even a key yet, but I'll make a key for you as well. How's that? I'll make a key and I'll send that out tomorrow as well. Have a good night, everyone. I'll stick around in the chat. I'll send you the notes soon. Here's the link one last time, and I'll see you later.